So this is essentially what we talked about yesterday. We went into pretty good detail talking about kinetic energy versus potential energy. So we won't obviously do that again today. But I do want to talk about energy. And then depending on how we are for time, I want to focus specifically on heat energy. Talk about heat kind of in more detail. But when we talk about energy as it relates to science, we're talking about anything that has the capacity to do work, right? And work is done anytime a force is applied to something, set it in motion. So again, like I said yesterday, energy doesn't mean that something is actively moving or actively generating um, energy, actively generating or doing work. It just means that something has the capacity. So when we talked about yesterday's example, right, when I cut the lights off, that doesn't mean I'm destroying that energy or that the light bulbs no longer have energy. It's just stored in a different way. And that's kind of what we're going to talk about more today than the whole kinetic versus potential energy thing. But just to quickly kind of recap what kinetic and potential energy are so you understand that going forward. Kinetic energy is the energy of an object's motion, right? So something doesn't have kinetic energy unless it's moving, right? Whereas potential energy, just think of it essentially as stored up energy, right? So kind of a bad example, right? But if I cut the lights off, right? Now the lights aren't generating kinetic energy because there's nothing actively happening, but it's stored up somewhere. When I go to turn on the lights, boom, now we have active kinetic energy. Okay, so that's all I really want to focus on in terms of review from yesterday. But I want to spend today kind of going over different forms that energy might take. And this isn't kind of an all-inclusive list. This is just kind of some examples. So we'll kind of go from there. So again, energy can take lots of forms. And one thing specifically, and we'll kind of get to it after we talk about these different forms, but energy can transfer from one form to the other. So getting ahead of myself. All right, so mechanical energy would be something that turns the axles of a car, or the blades of a fan, or the turbines of a windmill, or anything like that. Right? So that would be mechanical energy. Thermal energy would be exactly what it sounds like, energy from heat. So heat is essentially a form. When we use the word heat is a type of energy. Okay? It's specifically that energy that can change matter from solid to liquid or liquid to gas. Right? Chemical energy. Chemical energy is potential energy stored in the bonds between atoms of a substance. Plants and animals store and release chemical energy. Think of chemical energy, that's like a real sciencey definition. But think of chemical energy more like when you eat something, right? Your body breaks down that food and energy is released from it. And that's the reason why animals and humans, we need food to live, right? Because if we're tired or we feel hungry, we eat, and then we get energized from it. That's literally because we are taking the energy from that food and it's breaking down and it's transferred into energy that we can then use. Right? So chemical energy would be like energy from breaking down. Right? There's other examples, but that's, I think, and again, these aren't all the different types of energy, but just kind of the only ones we're really going to focus on. Nuclear energy would be energy stored in the nucleus of an atom, and it is released when those nuclei are broken apart. Okay, so without going way back to when we were talking about atoms and whatnot last week, essentially an atom is the smallest form of matter that we have, and so atoms aren't designed necessarily to be broken apart by definition. That's as small as we can get. But we can manipulate those atoms to actually break them apart, and they release a huge amount of energy when that happens, and then they essentially come back together because they're not really designed, or they're not designed at all, to be broken apart. So nuclear energy is essentially breaking those atoms apart, and you get a huge burst of energy, and then they come back together, and so you can reproduce it over and over. And that's why nuclear energy is a form of renewable, which we'll talk about renewable versus non-renewable energy much. Light energy is exactly what it sounds like, creating an image by causing chemicals on a piece of film to react, or literally, light we receive either from light bulbs or fire or the sun, right? So light energy can take a lot of different shapes or forms and can look literally, when we look out and see light, that's a form of energy. And then electrical energy is exactly what it sounds like. Think anything that requires electricity. That could be powering appliance, so on. We could go on and on down. Okay, but kind of what I wanted you to kind of think about and take away from this isn't necessarily to remember all these different types. It's simply to know that energy can be converted from one form to another. In other words, energy can go from chemical energy to heat energy to mechanical energy. The example, or I lose track of when we talk, but we were talking about the cooking of an egg, and how I think it was when we were talking about chemical reactions a little bit. But the reason I bring that up is there's a lot of energy that goes into cooking an egg. So, for example, first we have to, and let's say for this example, we're going to cook it on an electric stove. So, let's say that energy starts out as electrical energy, right? The stove isn't going to turn on unless it's plugged into electricity. So, we have energy that is harnessed in the electrical wiring. Okay, we turn on the burner, right? And now that electrical energy has now changed into heat energy. It hasn't come out of nowhere. It came from electrical energy actually transferring and changing into heat energy. Then that heat energy is transferred into the egg. The egg absorbs that heat and undergoes chemical changes and cooks the egg. Right? And then we eat that egg, and that egg gets broken down and turned into chemical energy. So I'm not going to go on down, you could follow that chain forever, because if you look down here on the bottom of this page, right, energy can be converted from different form to form to form and just keep going. But energy cannot be created or destroyed. I got thrown off by the wording looking at it. It says energy can neither be created or destroyed. Same thing. Energy cannot be produced out of thin air, and it can't just disappear. Okay? That's the law of conservation of energy. So in other words, when I cut the light switch off, I'm not destroying energy. That energy is just changing form. And when I turn the light switch on, I'm not magically creating new energy. That energy already existed, it's just being transferred into light energy that we then see, right? So think of energy like an endless cycle. It can transfer from one thing to the other, to the other, to the other, to the other, but it doesn't really ever go away or be destroyed, and it doesn't magically become magically created. So with that said, I'm going to focus kind of the rest of class talking about heat energy, but since we're kind of segueing here, it's a good time to just reiterate, if you do have questions for Caleb or myself, ask us in the chat. And if you do want to ask any questions, please feel free to message me, and we can open up the audio and video at the end of class if you have questions. Okay. All right. So with that said, let's look at heat specifically. So again, heat is a form of energy, right? Thermal energy. energy and the ability to change something from solid to liquid or liquid to gas. Okay? When we talk about temperature, the word temperature just is a measurement of that, and it's actually measuring the kinetic energy of the particles in a substance. So it's actually, we can't necessarily see those particles, but when you add heat, you energize molecules, right? And they start moving around. An example of that would be, if you imagine, or if you've ever seen like an old school mercury thermometer, maybe you have, that looks like a meter, where, there's a little bulb at the bottom and then it goes up and then there's little lines for the temperature, right? Essentially what's happening in that is as the temperature increases, the molecules in that mercury or in that liquid inside of the thermometer expand and heat up and start to move around and generate more kinetic energy. So the level goes up and matches to whatever that number is, right? So when it's 70 degrees, that that little line is up to the 70, right? Whereas if it gets cold, the molecules in that mercury condense, slow down, they're not moving as much, and that's why that mercury is lower. Right? So if you don't know what the hell I'm talking about, then you've never seen an old thermometer, I don't blame you, right? That's just an example. So when we talk about heat, and this is kind of the substance of what I want to get at, is there are essentially three ways heat gets transferred from one thing to the other. Okay? Conduction, convection, and radiation. So let's go through those three things and then go from there. So first is, and I'm going to go just kind of in order, conduction. Conduction is direct transfer of heat. So in other words, if you imagine a campfire, right? You stick your hand in the flame and you touch your hand to the flame, that's conduction, right? You're directly getting the heat from the flame, right? Or if you touch the burner on a stove, you are directly transferring that heat energy to your hand, right? So conduction is direct contact with heat. Convection is simply heating up the air around something, right? So in other words, if you put your hand near the fire, it's a lot hotter closer up to the fire, right? But it's obviously not as hot as if you stick your hand in the fire, right? But what you're essentially feeling is that fire is heating up the air around your hand, and your hand is hot. Same thing with a burner. You can put your hand near that burner and you can start to feel that heat. And that is convection. Just like if you've heard of, or if you're familiar with the term convection oven, when you cook something in the oven, you're not applying direct heat to that food. Right? Whereas if you are cooking on like a skillet on a stovetop, that skillet is hot. You put something on the hot skillet, and you're cooking it with conduction, right? Direct heat. But in an oven, when you turn the oven up to 400 degrees, and you stick something in there, the only thing that's hot that you can see in that oven, I mean, there's burners on top and bottom, but the food is being cooked because the air temperature inside that oven is 400 degrees, and that's convection. Okay. So again, if we go back to thinking of this like a campfire, conduction is sticking your hand in the oven. Conduction is sticking your hand in the oven. Convection, standing real close to the fire and feeling that warmth all around. Okay. Now, radiation is a little bit different, right? So radiation is essentially your body absorbing electromagnetic waves. Okay. Now, what does that mean, and what does that look like from a non-science standpoint, right? And we'll come back to our campfire example in a minute, but think about the sun, okay? So the sun is this huge ball of energy, and we receive lots of heat, obviously, from the sun, okay? Now, the sun is far away, and so the sun isn't providing nearly as much convection heating as it is just radiation. And a way to think about that is on a hot day, the reason why it's cooler in the shade than in the sun doesn't have to do with air temperature. It has to do with the amount of radiation that your body receives when you're in direct sunlight versus when you're not, right? So, if you're in shade, it might still be the same temperature, but when you step out into the sun, your body gets hit by all of these waves of radiation, and you feel a lot hotter. So back to our campfire example, if, again, conduction is sticking your hand in the fire, convection is standing near the fire and the air around you is warm, keeping you warm. If you stand further back from the fire, right, the air temperature around you is cold, or colder, right? But you feel warmth up, radiating against your body. That's the reason why, if you're standing, back off the fire, your front is warm, but oftentimes, sometimes your back might be cold. It's not because the air temperature is colder there than it is here. It's because you're directly facing the fire and you're receiving waves of radiation. Right? So it's the same way a microwave. You cook food in the microwave. The reason it cooks so fast is because you're cooking with radiation. So what I mean by that is a microwave doesn't take the time to heat up the air inside the microwave. That's why when you open the microwave after you cook something, it's not hot, right? That's because it's not cooking with convection. It's taking waves of radiation directly from that light bulb, and that food is absorbing it. And that's why it cooks so fast, and that's why it isn't hot inside that microwave, okay? So, again, hopefully that kind of makes sense. And just remember, take away from this the three different types: conduction, convection, radiation. And again, kind of down here on the bottom, I just want to talk about a couple things, and then we will jump into some practice questions. So again, the transfer of thermal energy is known as heat, right? And one thing I want to emphasize is that the flow of heat, in other words, the flow of energy between substances at different temperatures, always flows from hotter to cold. Right? In other words, if let me think of a good way to emphasize what I'm saying. So if you put water in, let's first go the opposite way, the obvious way, right? So if I want to heat up a pot of water, right, I take cold water and I put it on the stove. The flow of energy is from hot to cold. In other words, the burner heats that water up until eventually the water will match the temperature of the heat of the flame, right? Or in water's case, until it reaches boil. Right? But essentially, if you heat something up and you have something cold, something hot, they'll eventually the heat energy will increase until those two things balance out. In other words, until they become the same temperature, right? So it's like if you had a cup of hot water and a cup of cold water and you pour them together, the hot water would add energy to the cold water, and essentially it would eventually work out to where the water is the same temperature, right? Somewhere in between those two. Okay. Now, the reason I mention that is because when you cool something off, or when you freeze something, the energy flow isn't going from cold to hot, right? So when you take hot water and you put it in the freezer, it eventually freezes. The reason for that is that the heat in that hot cup of water basically gets overwhelmed or releases its heat energy, and eventually the equilibrium is such that that water gets frozen eventually because the energy there's not enough, right? But I realize that as I'm saying that's kind of confusing. So just take away from this that energy only flows from hot to cold. All right, so let's see, we've got plenty of time. Let's look at a couple practice questions. So let me Give me just a second. So bear with me here. So let me pull up. Sorry for this. I meant to have ready for us. Okay, so hopefully you can see these questions. All right, so we did a couple of these yesterday, and we skipped around others. So let's first look at number 2. So number 2, and I'll zoom in here. Number 2 deals with the transfer of energy, or not necessarily the transfer of energy, but the changing form. Okay, so number 2 says, during a power outage, George relied upon his flashlight to move around his home. The flashlight is constructed with wires and a light bulb enclosed in a plastic casing. It requires batteries to operate. Write in the 3 types of energy involved in turning on and using the flashlight. Okay, so think about that for a second. Okay? 3 of those options are required for that sequence of events to happen. Right? And while we're doing that, I'm going to pull up the explanation for this. So I make sure I don't confuse myself. Think about that for a minute, and then we will. Find it. Bear with me. Okay, so the first would be chemical energy. So the batteries use chemical energy because they are, the way a battery works, right, is it's, you know, a bunch of chemicals that help generate energy. That's why a battery can work independent of electrical wiring. But what do those batteries generate? They generate electricity, right? So that chemical energy stored in the battery, once it reacts with another battery and with the little, you know, pieces that you, the little conductors, right? That chemical energy then gets turned into electrical energy. So there's our first 2. So it starts as chemical and moves to electrical. And then lastly, what does the electricity in that flashlight do when we turn the switch? Right? It activates the electricity, but then electricity flows to the light bulb, and that light bulb turns on, and we end up with light energy. Right? So those 3 . So those are the main 3, right, that would be involved in turning on and using that flashlight. Okay, so let's go ahead and do, we have enough time? Let's do a couple more. So let's do number 3. And see how we do. So number 3 says, an oak tree may grow very tall, very slowly. It may take the tree 100 years to absorb light energy and store it as chemical energy, yet only a single winter to be turned into heat energy in someone's wood stove. Which concept does this best relate to? A, work, B, power, C, force, D, kinetic energy. So, just to kind of reiterate what it's getting at, and again, if you weren't here for yesterday, then some of these terms might not be as familiar. But essentially, it's saying that it takes a tree hundreds of years to slowly absorb light energy and store it as chemical energy and grow and grow and grow. But it doesn't take long to burn that tree and turn it into heat. Right? That transition happens. Okay? So again, we talked some about all these terms yesterday, but the one that it's most specifically getting at here is power, because power is defined as the rate of doing or how fast work is being done. So in a different example, away from this tree, right? If we talk about getting somewhere, right? So if you need to go to the store, okay, walk, ride a bike, drive a car. Driving a car uses the most power. In other words, it gets you there the fastest, quickest way of doing it. Or maybe a better way to look at this is you could let's take out the factors of the bike and the car and just talk about you could walk, you could jog, or you could run right to the store. What's going to get you there fastest? Well, if you can sustain it, run it, right? If you can't, then that's a different story, right? But think about how tired you would be if you ran all the way to the store versus walking all the way. It might take you longer, but you're expelling less energy. So that's the idea of power here. Is that the rate of either doing something or the rate of consuming energy. So the power is much greater when we talk about burning that wood, right? It generates a lot of energy quickly, whereas the tree growing, right, uses less energy over time. It's just a slower process, okay? And let's do, as long as real quickly, since it talks about heat, goes over heat, let's look at number 6 and see if we can answer number 6. And then we'll end. So, okay, so number 6 says that heat energy is present in all matter in the form of the kinetic energy of its atoms and molecules. Right. So what that essentially means, and when we talked about, I'm not sure if you were there or remember when we talked about solids, liquids, and gases, right? But essentially particles in a solid are suspended in motion, right? They're not moving. They don't have kinetic energy. They have very little. But in a liquid, those molecules start to move around even more. And in a gas, they move around a lot more, okay? And that's essentially what we're talking about, right? That the kinetic energy is greater when in a liquid than a solid, and then in a gas than a liquid. So, with that being said, heat energy can pass from one place to another through conduction. Transfer of kinetic energy from molecules of greater motion, hot areas, to molecules of lesser motion. Solid metals like silver and copper are good conductors of heat energy, whereas gases like air are poor conductors. What is the reason that air is a poor conductor of heat? Okay, so this is a tough question, and maybe not even one I would necessarily expect anyone to get without some. Okay? But it's a good question to try to practice. You know, what happens, or what do we do when we get a question we maybe don't believe? Right? So, A, the molecules in air are very far apart. B, the molecules in air are very large. C, the molecules in air do not move. D, the molecules in air are very small. All right, so again, if you were here last week or you did listen to the lesson on states of matter, when we talked about particles and how they act in solids, liquids, and gases, this might be something that you could get the answer to. If not, it'll be pretty difficult. But the first thing that I would do if I were taking a test and got this question would be, I don't think molecules and gases are different sizes. So very large and very small, I would throw them out, especially because it doesn't mention anything up here, right? So B and D I would throw out. Now, A and C are kind of the two that I would maybe focus on. A says the molecules in air are far apart. C, the molecules in air do not move. So if you got that far, right, if you were able to maybe eliminate B and D, then you could think about it in terms of what it says up here. Okay? Heat energy is present in all matter in the form of kinetic energy, right? So solids have less kinetic energy, liquids have more, gases have a lot. Remember, kinetic energy is the energy of motion. So molecules in air move a lot. They aren't suspended, right? Only molecules in solids stay still, right? So C doesn't make sense, so A has to be right. A is in this right answer, right? The reason that air is a poor conductor of heat is because the molecules are really far apart. So, and that might make no sense, that might make some sense, hopefully it does. But that's the reason why if you heat up a metal surface, right? So if you don't usually, well, let's say you have a metal frying pan, right? You heat that frying pan up and you turn the heat off, that metal stays hot for a long time, right? But if you take air and you heat that air up to the same temperature as the frying pan, you get air really hot, right? The minute you cut off the heat source, the air cools off fast. So that's what they're talking about here, right? Metal keeps its heat much longer than air does. And that comes back to the reason behind that is because the molecules are closer together in a solid than they are in a gas. All right. So again, hopefully that wasn't totally confusing for those of you that weren't here yesterday or haven't listened to any of the old lessons. We're going to go ahead and stop for the day there. Tomorrow, we will talk a little bit about Newton's laws and go over some laws of motion. And next week, hopefully we'll get to the point where we wrap up physical science and we move on to talk about some different areas. So hopefully that was somewhat helpful. Again, if you have any questions, always ask me. If you need help that you're not getting, just ask and I'll make sure that you get it, okay? So with that said, I'll go ahead and stop class day there and I will see you all tomorrow.